Hi, good morning, good afternoon, good evening, depending on where you are today. Thanks for attending Aerospike's 2021 Virtual Summit. I very much hope you're enjoying the event so far. My name's Ken Tune. I'm a member of the Solution Architecture team at Aerospike, and I'm going to be talking to you today about the Aerospike List and Map API, also known as the Complex Data Type or CDT API. This API is something that's very much unique to Aerospike. It basically lets you execute document-oriented operations server-side in a highly performant way. It was originally created in response to customer need, so it's very much a feature that's useful and applicable. It's also very much a distinguishing feature for Aerospike, so you won't find this built into other nominally similar databases. And today I'm going to help you understand why it's useful by letting you see how it's applied in the context of an actual customer problem. And specifically, I'm going to talk about fraud reduction applications and how the List and Map API can be used to enormously streamline the types of calculations that are commonplace in that area. So we're going to look at how the CDT API in the context of fraud reduction will let you reduce your read count substantially as against a database which doesn't offer a similar API. So why is reducing read count good? Well, your overall decision time in a fraud application will be strongly affected by the number of reads that you do. If you reduce the number of reads, you'll reduce the decision time. And this is good because in the world of payments, timescales are short. Typically, they'll need to be wrapped up in under a second. If you have too many reads in your application and a very fixed, tight SLA, such as the one we're describing, if you can't optimize those reads, you might have to try and reduce their overall number, which will mean less accurate models because you'll be able to feed less data into them. And the flip side of that is if you can effectively get more data per read, then you'll be able to deploy more sophisticated models. Additionally, by being very tight and controlled about the reads that you do, you're going to be much better able to work to strict SLAs. It's going to be a hands-on talk today. So I'm going to look at a particular type of requirement that we see in fraud reduction, and I'm going to let you see iteratively how we can move from a high read count method to a low read count method via a succession of steps which use the List and Map API. We're going to be looking at actual code, and for each code sample that I show you, I'll also be showing outputs to help you sort of see what it actually does, which will help you gain a much better understanding of what is going on. So here's the particular calculation that we're going to look at. A key quantity in fraud models is average spend, but not just average spend full stop, average spend over different periods to allow for the fact that customer spend over time isn't a constant. It will increase, for example, at Christmas, during holidays, or perhaps when you're buying a house, some sort of substantial event such as that. And we need to allow for that variation, otherwise our model is going to be more likely to flag genuine activity as fraudulent. So the averages, plural, that I'm describing, they are going to be based on sliding windows. So when we're looking at an incoming transaction, we're always looking back in time from the time at which that transaction was made, which is almost always exactly the present time. So to compute floating rate averages, which are the averages that we need to feed into the model, we need to look back using different periods. And the sort of slide spells that out to a certain extent. And these are very typical in the world of fraud reduction. I might choose to look back from the present time, 24 hours, 3 days, 7 days, 14, 30, most likely 90 as well. So if it's May the 5th today and 0923 precisely, to get the average spend over the last 24 hours, we need to go back to the 4th of May at 0923. Average spend over the last 3 days, we need to go back to the 2nd of May, same time, 7-day average spend, 0923 on the 28th of April. So the problem is that we need to perform these calculations, we need to look up all the transactions within that time period. So that's within the last 30 days, and most likely within the last 90 days, in order to compute these floating rate averages. So the reason we need to do that is that we can't pre-compute them because the window is constantly changing. Okay, and as you can quickly see, that's a lot of reads. So if we have 4 transactions a day on average, if we were computing a floating average over a 90-day period, that would be 360 reads, which is, that's a lot of activity. Even at 1 millisecond per read, if you're doing them sequentially, you've used up 360 milliseconds of processing time right there, were you to do these things serially. So really, if you will, the problem that we're going to look at today is how we can start from this relatively naive position and get to something which is much more performant, much more optimized. And I'm going to show you how the list and map API helps you do that. All right, so first thing we're going to do, I've said that floating window calculations are not straightforward, and the implication there, ever so slightly, is that fixed window calculations are tractable to a certain extent, certainly easier to address. Okay, so let's consider what we might do to optimize the calculation of averages across fixed periods, so periods which are associated with beginning and end of days. So if I was to look at how I might optimize fixed window calculations over different periods, such as 3, 5, 7 days, and I wanted to do some optimization, what I can do is, rather than looking at every transaction in that period every time, I can, on each integral, on each whole day in my window, I can do some pre-computation. Specifically, the pre-computation that I'm going to do is I'm going to keep a track of, for each day, for each customer, total spend for that customer and the number of transactions that occurred on that particular day. So if I keep track of those two things for each day, then if I'm looking to answer the question, well, what is my average spend across 7 consecutive days, I can reduce the number of lookups that I need to do by instead looking at these aggregate records. So for instance, to work out the average spend across 7 days, I look at the total spend on each of those days 1 to 7, add it all together. I also look up the total number of transactions across those days, which I get by looking up the total number of transactions for each of those days and adding them together, and then dividing total spend by total number of transactions, which is the way averages work to get the answer. So that's expressed using the sigma notation on the slide. But if you're not familiar with it, hopefully that sort of verbal explanation conveys the idea reasonably well. So what I've done, if you will, is I've used a MapReduce type approach. So I can use MapReduce for averages. The key thing is that you can't take averages of averages, but if you track the thing that's in the numerator of your average, the thing that's in the denominator of your average, then you can partition up the calculations in this way. So immediately, the nice thing about what we've done here is that if we're looking at calculating averages over a consecutive number of integral days, the number of lookups is reduced substantially. So the number of lookups I need to do for a given average calculation is equal to the number of days in the window in question, rather than the number of days multiplied by the average number of transactions. So if I was computing the 7-day average, I need to look up the amounts and the transaction counts for each of those 7 days, rather than each of the transactions. If I put some numbers against this, if I had to compute a 30-day average with an average number of 5 transactions per day, if I did that in a naive way, I'd have to look up details of 150 transactions. Whereas if I pre-compute these aggregates, then I've reduced my number of lookups to 30, because I just need to look up the data corresponding to the 30 days in question. Okay, so let's have a little look at how we do that in code, and specifically making use of the tooling that the List and Map API gives us. So what we'll be doing when a transaction comes in, we'll be updating our aggregates in real time, which is kind of nice. Note that we're not doing this using sort of complicated batch-oriented routine. We will have a record for each customer for each day. So the key to the record, which is the function daily aggregate error key, is a function of the customer ID and the transaction date. So I find the record corresponding to that transaction, which is basically corresponds to the truncated date. So I've got a record for each day for each customer. So what's going on in this function? So I'm updating a record, and then I'm updating 2 quantities within that record. So the record is a map. There's 2 keys in the map. One's keeping track of the total amount, and the other's keeping track of the overall count. You can see that I'm effectively incrementing the count, and I'm by 1, and I'm increasing the amount spent so far this day by the amount of the new transaction. And what's critical to note is that this is all happening in a single operation, right? So I'm not having to make multiple calls. I'm showing you a relatively simple example of the List and Map API being used here. It's just 2 operations, but actually it could be an arbitrary number of operations that are taking place here. They'll all take place very efficiently, so you immediately start to get a feeling for the sort of the power of this method. Okay, so this will become clearer, or clearer still, hopefully, if we look at an example of this method being used in practice. So I've got 5 transactions that I'm creating here explicitly. They're all for today's date. They've got various sort of randomish amounts, and we can assume that as those transactions came in, they were all pushed through the update daily aggregate function that we've just discussed. So if I select today's record as of the time that I prepared these slides, 5th of May, overall, at the end of having processed these 5 transactions, this is what I'm going to get. I'm going to get a record which has tracked the transaction count and has tracked the overall spend. Just to re-emphasize that I'm doing this on an ongoing basis, right? So it's not it hasn't come out of a batch process. It's being updated in real time. The reason that that's important is that batch processes are difficult to manage very often. So because they run effectively asynchronously, there's always the question as to, did it start? Did it finish? If it didn't finish and it failed halfway through, how do you deal with that? How do you deal with processes that for some reason didn't start? It's a messy kind of raft of considerations. So having something that updates in real time is often just a lot easier to manage and less prone to difficulties. So that is a kind of critical element of what we're doing here. So let's just look at what this improvement actually gives us. So for this particular computation, so averages taken over fixed periods, we've reduced the number of lookups by a factor equal to the average transaction count per day. So reduced it by a factor of 5 if you use the numbers that I showed earlier. It's really important to note that this is on average, the level of improvement I would have got. So some accounts will have much higher transaction rates, and of course that will be variable. There will be periods where accounts have high transaction rates and periods when they revert to the mean. So for those customers, the level of improvement that we get by just doing this relatively simple thing is potentially much more than 5, and these are the customers that are potentially going to cause us difficulties, because it's the deviations from the mean, it's the long tails that will potentially, they will always be the first thing that mean that we potentially break our SLAs. And we've gone from having an unpredictable number of reads, because what we don't know is the average number of transactions per customer, to a predictable number of reads, because what we do know is we know the number of days in scope every time. So that's actually quite a profound change. So this is the first sort of step of 5 in this presentation, which means therefore that what we've done isn't perfect. It's not the end of the story. So it's useful, of course, to look at what is wrong or incomplete here. So the first thing to note is that although I've reduced my reads to the number of days in scope, so 30 days if we're doing if we need to take averages over 30 days, we're still needing to do 30 reads. Also, what I've done is just streamlining computations for fixed period averages rather than floating period averages, which is what we ultimately need to do. So the next step in the process is to look at how we reduce the number of reads yet further. And if you will, the answer is probably sort of glaringly obvious, having seen the example. Instead of just ending up with this relatively small record which tracks spending on a daily basis, why don't we just put all that information into one record, and then when we need that information we just pull it back in a single read. It's an obvious optimization. So what we'll do next is we'll see how we do that using the tooling that the List and Map API provides. Okay, so the function you're looking at here, update daily aggregate 2, is putting the transaction information in a single overall record. It will still be sort of executed in the iterative way that we saw previously. The first thing you'll see about it is that the key has changed. So it was previously a function of customer ID and date. It's no longer a function of date, because we'll just have one such record per customer. In terms of what's happening in the function, the first map operation call, that creates a map for the day of the incoming transaction. Right. So here's the key to that. So this date formatter basically truncates the date time, and you see that we're putting in a new map if one doesn't exist already. The next two things you see pretty much do the same thing as before. So we're updating the total spend for that day and the transaction count for that day. In fact, it's exactly the same as before. But what's different is these operations now have what we call a context. That's the CTX call that you see here and here. So what that says is don't update the map at the top level. There's a context to this operation, and the context is update a map within a map, and we indicate that by saying that the context is a map key, and that key is the truncated timestamp of the transaction that's coming in. And if this isn't clear, then it will hopefully be clear on the next slide to what's happening. Other things to note about what you're seeing here: everything is still being done in a single operation, and point 5 on the slide, I'm just sort of hammering it home. All this aggregate information is now in a single map, in a single record. Okay, so what do we see? What do we see in practice? So this is similar test code to what we saw before. So I've explicitly created 6 transactions, but the difference is that I'm creating them for different dates. So these transactions were for the 5th of May. I'm subtracting 1 from that date, so these transactions are for the 4th of May, and then I'm running them through the update daily aggregate function, and what I end up with, if I select from customer aggregates, and this is again an important-ish part of best practice, if you will, is that you should nicely label all the records that you have in your database. So I've put it in the test namespace, but I've called it customer aggregates. The key to the overall record is customer ID based, so there's no date component to that. Then inside the record, I'm tracking total spend on a daily basis and transaction velocity on a daily basis, and I'm indexing that by the dates in question. So the point of this is that this will now enable me to do the same calculation that I was doing previously by putting together all this information in order to calculate the averages. But the key is that it's now all in one record, rather than previously it was for each day the separate record. So numerically, what we've done, just rolling with the numbers we've used so far, the naive solution would have involved doing 150 lookups to calculate the average over a 30-day period. I'm now in a position where I can pull back all that information just in a single read, right? So that's a considerable transformation, 150 to 1. That's an improvement of 2+ orders of magnitude. So between 2 and 3. So the actual answer will be log base 10 of 150, whatever that is. The improvement we get, that is the average level of improvement. So for some customers, or for some customers at certain times, the level of improvement will be better than that, because the number of reads we would have had to do using the naive method was unpredictable, because it's dependent upon the average number of transactions for that customer, which is an unknown. So not only have we substantially improved in the number of reads that we're doing, but we've moved it again to a point where it's a predictable number of reads, and it happens to be a single read, and arguably you can't get much lower than that. So this is step 2 of 5 in the presentation. So therefore there's got to be some reason why what we've done so far isn't perfect. One obvious-ish point to think about is that what I'm doing is I'm adding records to my master record on a daily basis, and that means that record will be growing in size to a potentially unchecked extent, and it's not the case that a single record can grow in size forever. So within Aerospike there is an upper limit to a single record. It can be up to 8 megabytes, but nevertheless there is an upper limit, so we need to do something about that. And then just keeping it on the radar, what we're talking about here is calculations associated with fixed windows rather than floating windows, which is what we ultimately need. So I'm going to address point 2 in the next iteration of the approach. How do we stop records from growing in an unchecked way? So we do that by essentially pruning the record. And what's important to know is that the list and map API gives you the tooling to do this. So although we do, it's not necessarily a given that something like this might be available. It's just demonstrating the power of the list and map API and demonstrating that over time the things we need to do have been thought about very carefully. So it's no accident that this happens to be here. So we've got a third function in our chain of sample functions. I've called it update daily aggregate 3. This function is completely identical to the previous function that we looked at, update daily aggregate 2. The only difference is the addition of a single line at the bottom, so the boxed remove by index range function, and that's what we're going to use to do the list truncation. So we've been using ordered maps. What that means is the most recent key. The keys are sorted in string order, and I've been using a date format in such a way that the most recent timestamp will sort to the front, the least recent to the back. So what this remove by index range operation does is it chooses a number of days to keep, which would typically be something like 90 in practice, and then the -1 lets us essentially discard everything beyond that limit. So I think it's going to become a bit clearer if we see the results of that in practice. So we've got some test code here. What I'm going to do is I'm going to work over a 10-day period, generating 5 random transactions per day. Every time a transaction comes in, I'm going to be running it through this update daily aggregate 3 function. And we've got 2 outputs on the slide, and we've got one that's the result that you'd see if you didn't have list truncation, and the second one shows you what you get if you effectively comment in the new line that I just showed you. To make it sort of super clear what's going on, I chose to set my days to keep variable at 3. Otherwise, I'd have to produce quite large outputs if I was doing something that was kind of realistic and kept 30 days history, 90 days. 30 days to keep 3 makes it much clearer what's going on. If I ran my test code over generating transactions over the 10-day period, you'd end up with a map which looks like that. So it would have effectively 10 entries. Running it through update daily aggregate 3 will result in the list, the list of maps being kept to no more than a specific size, and you can see that we've just got 3 entries here rather than the 10 that I would have got had I not done the list truncation. So hopefully that's clear. Let's just check where we've got to. Again, if we were working with fixed windows, we'd have reached the point where we could compute any average over any number of days by just doing a single read, having aggregated all the information we need into a single record. And we've also dealt with the pruning problem. Okay, the next thing that we're going to do is we're going to go back to the fact that we're not dealing with fixed windows. With respect to the averages that we're calculating, we need to actually work with sliding windows. So what we've done so far does help us. If you think about it, kind of the bulk of the calculation has been done. But we also need to address the fact that the floating windows give rise to what you might call stub periods. So if I have a transaction that comes in at 9:23, it's 9:23, it's the 5th of May, and I'm computing the average spend over exactly 30 days, then I've got the integral 29 days, which is sort of somewhat form the sort of brunt of the middle of the data. But I've also got the stub period, which is basically the period between the midnight just struck and the time now. So I need to pull in all the transactions that happened in that period. But I also need to pull in all the transactions between 9:23 on the 5th of April and the midnight between the 5th of April and the 6th of April in order to get my calculation absolutely accurate. So it's those kind of like messy stub periods that make this a harder problem than dealing with windows which are fixed against date boundaries. Okay, so well, there's obviously a naive way of doing this, but we can move away from the naive method and do something slightly smarter. So the naive way of doing it. So first of all, the transactions for today, for like the stub period associated with today, like the time between now and the midnight that was just struck, they're kind of less. That's kind of less problematic because I just need to read in all the stuff that's happened today, and if you will, I can't sort of really optimize that away in any fashion. I'm always going to need to read in all the stuff that's happened between midnight just struck and the present time. Where there is scope for optimization is the stubs associated with the far end of the floating window. So we said that if I need to compute the 30-day floating average and it's the 5th of May and it's 9:23, then I need to pull in all the transactions between 9:23 on the 5th of April and midnight between 5th of April and the 6th of April. The naive approach that I alluded to is, well, I could just pull in all the transactions for the 5th of April and just ignore the ones that fall outside the period that I'm interested in. But if you think about that, on average, that's going to double the number of reads that I need to do. And sometimes sort of more than that. So it's certainly a very inefficient thing to do. So if I'm saying it's inefficient, well, what's the sort of slightly smarter answer? And the slightly smarter answer is that I keep as the transactions are coming in, I keep a list of all those transactions, and then I have a new list for every day for every customer. But when I access my list, I just pull back the things that correspond to the period that I'm interested in. So I can do that if I'm kind of smart and premeditated about the way in which I model my data. The List Map API, you'll not be surprised to hear, lets you do that. Okay, so here's the code sort of showing that in a bit more detail. There's two parts of this code. So there's the putting data into the database, and then there's the kind of getting the data out of the database. So the modeling, if you will, is there's a putting of the data into the database, but then there's a little bit of smartness associated with retrieving the data, which gives us the optimization that I'm talking about. So the first thing is I'm maintaining for every day for every customer a list of transactions, transaction IDs, and the way I'm modeling that is that the list is actually a map, and the map is indexed by the timestamp of the transactions, and the list and map API will let me look up elements in that map by assuming that the keys are ordered in some way, which in fact they are. So this is why this is a useful thing to do. So in code terms, it's pretty trivial. It's doing what the output shows. I've used a different datetime formatter here. So previously, I've been concerned with the integral part of the date with respect to creating keys, but actually I need the full datetime here. So you can't sort of see the detail behind this, but it's a formatter which doesn't truncate the date. It gives me the full datetime sort of element of that. So every transaction that comes in will be run through this store transaction for customer one. I'm putting it in a set which I call transaction lists. The key to elements in that set is comprised of customer ID and date, because I have a different record for every date for every customer. And what I end up with is this map, which is the transaction IDs, which are indexed by timestamps. So as I said, the important thing, if you will, is not kind of how I'm storing the data, but how I'm making use of it. And here I'm introducing a new element of the list and map API. We're going to be making use of this GetByKeyRange function. So as I said, that assumes that the keys to the map can be sort of ordered in some way, and then that makes use of the ordering. The way I've chosen to express the dates naturally orders the keys in datetime order. So you can see that there are some ways of formatting dates that wouldn't do that, and there are some ways that do. So if, typically if the formatting is year, month, day, hour, minute, etc., then you'll get the ordering that you need. So because I've got sort of ordering of the keys within the map, I can now use this GetByKeyRange function. As we discussed, this, if you will, so two types of stub to consider for a particular date time. There's the stub, which corresponds to all the records before the time from between midnight elapsed and the timestamp, and the other stub is the complement of that represents the time between the timestamp and then the midnight to come. So this retrieve transactions before date time uses the GetByKeyRange function, and the constraints that I'm feeding into this function are the truncated date time and then the untruncated date time, so if you will, between midnight and 09:23, and this function will retrieve the values corresponding to the keys that match those constraints. So to make that concrete, if I was running this function for customer ID 1 for date time 3rd of May 12:25, it would pull back transaction IDs 1,041 and 1,043, and you can see looking at the slide that those are the right values. So this one will not be brought back because 12:49 comes after 12:25. The next slide shows you the function that you'd actually look at, you'd actually need in practice. So the stubs corresponding to the sort of most far out day. So if I was doing a 30-day average, it's the 5th of May, I'd need, and it was 9:23, I'd need all the records between 9:23 on the 5th of April and midnight between the 5th of April and the 6th of April. So I'd actually need this RetrieveTransactionsAfterDateTime function, and it's exactly the same idea. Exactly the same idea. I'm going from 9:23 to the midnight to come. So I take my date, I truncate it, I add 1. That gives me my far constraint. And if we're assuming that my transaction history for customer 1 for the 1st of May in terms of transaction IDs and timestamps looks like what I ended up with in the transaction list set, courtesy of the update aggregate function that we've been discussing. If I run this retrieve transactions after date time, it will retrieve transaction IDs 1,034,000, 33, and 30 because they all come after 12/25 on the 1st of May. Again, this is just returning the values of the map. Map return type can be various things. You could return the keys, you could return the keys and the values. We actually only interested in the values. Okay, so to put these different pieces together, calculating averages associated with floating windows, for the most part, we can get the data we need from this sort of single master record that we discussed in step 2, but doesn't get us to pinpoint accuracy. We need to take account of these stub periods if we're working with floating averages, and this new way of updating, of creating the transaction lists, and then the functions that I showed you that retrieve correctly from the transaction lists allow us to accurately and optimally get all the information that we need. So we've completed the mandate, if you will, which is, so that's the plus. I guess the question is, well, are we done here? So sneak preview. This is step 4 of 5, so the answer has to be no. So why is the answer no, that we're not done yet? Well, these stub periods, they give rise to a significant number of reads in their own right. So kind of on average, each stub read will be half the average number of transactions per day. I mean, if you sort of hand-waving argument is to say, on average, the timestamp of your transaction is going to be exactly midday, so the transactions corresponding to the stub periods will be half the transactions for every day, so half the number of average transactions for the day at the end of the floating window. So if we're doing computations for n floating windows, and as I said, typically this is what you will do to get the information you need for your fraud models. You're going to be doing, with this method, to get the stub data, you're going to need to do n times f over 2 reads, right, to compute n floating rate averages. If we plug some numbers into that, if n is 5, f is 5, on average we're going to need to do 12.5 reads to pull in the transactions in the stub periods. I'm ignoring the stub period that corresponds to like the current day. I'll come back to that. So 12.5 reads. When you compare that to the single read that we need to do to get the brunt of our data, that kind of seems inefficient. The other thing to note is that the f is there in that calculation. So it's the number of reads we have to do is actually based on the average number of transactions per customer, and that half the time, by definition, that's going to be above average. So that could lead to needing to do far more than 12.5 reads, right? And again, that's going to be the thing, and that's going to bite you. So what would be nice to do would be to optimize this so that we're doing a predictable number of reads, and also we're doing fewer reads. So that's I'm going to show you how you do that in the final stage of the presentation. So you may well have got there before me. What I'm doing, or what I did in step 4, was I stored a transaction ID list, and then it's a case of which transactions do I need to look at. Oh, it's these transactions. Now I go away and look them up. Why not cut out the middle step, if you will, and instead of having to go away and looking up details of those particular transactions, why not pull out the information that we know we need in the first place and just store it in the record rather than storing the transaction ID. It's kind of obvious. You might ask, well, why don't we just store the full transactions in the first place, right? And that's a legitimate thing to do. So what I'm going to show you here is we just pull out the amounts, because that's all we need to compute average spend. So the reason for that, if you haven't worked in payments, payment records are actually much bigger than you might think. I mean, they're typically about 4K. So an awful lot of information goes in there. A lot of which, I think people who work in the area would agree, isn't necessarily terribly helpful, or it's not always terribly helpful. But they're significant records, so you can see that keeping those records in their entirety is potentially wasteful. And ultimately, it might result in aggregate records that are much, much bigger than you can actually process in practice. So what we do, when we're performing these sorts of optimizations, is we pull out the things that we need. So here, the one quantity I need to compute average spend is just the amount of the transaction. I don't need to track the number of transactions anymore, because I can figure that out by counting the number of amounts that I have. So rather than storing the transaction ID, and which was previously a simple key value relationship, I pull out the things that I need. For purposes of this presentation, I'm just going to pull out the amount of the transaction, but I could pull out other quantities. So again, I'm storing maps within maps rather than values within maps. So the fact that I can store a map within a map gives me the flexibility to put whatever quantity I want into that submap, whereas if it was pure kind of key value, I wouldn't be able to do that. And the point of this is that I'm then not having to go away and do those secondary lookups. Okay, so some more code. The function is called store transaction details for customer. I'm just storing the amount. First thing that I do, lines 2 and 3, I create a map, and then I put the things in the map that I'm interested in. Here it's just the transaction amount, and I put that in with a particular sort of static key, which is transaction amount. As it happens, you can see it in the output here. But then what I'm doing is I'm putting this submap in a much larger overall map. So the value in the larger map is the submap I've just created, and the key to that value is the full timestamp of the transaction. So to hopefully make that clearer, whereas previously we had for every customer for every day a list of transaction IDs, I basically have this abstracted transaction information, which is indexed by timestamp. So this is data that I might see for customer 1 for the 28th of April. And I can use this information in a similar way to the way that I used it previously. So I'm doing the same GetByKeyRange type lookup, so I'm pulling back the things that I'm interested in based on their timestamps. So retrieve amounts before date time corresponds to the stub before the timestamp, before this timestamp. And then this code here is just basically marshalling So it turns the data here into a list of amounts. So it's a list of longs, nothing more than that. So if I supply this timestamp coming into this function here, 1225, everything before 1225, that corresponds to amounts 134, 143, and 105. Correspondingly, the converse function, which is actually the one that I use in practice, is the retrieve amounts after date time, which is, you've now seen all this pretty much already. I'm using the GetByKeyRange NAP operation. The stub period is the period between the timestamp and the end of the day. I'm marshalling the information, I'm turning it into a list of amounts. If I call this function with this date time, it would return me all the records that have a timestamp which is after 1225, which will give me amounts 113 and 105. So if we put all these things together, if I want to compute n different floating rate averages, I can do that in n plus 2 reads, right? So a fixed number of reads. So the n is for the stubs at the end of each floating window, and then there's 2 more reads. There's one corresponding to the stub at the beginning of the window, which is the same stub every time, right? Because I've always got to look up data for the current day. And the last one in the n plus 2 is the data corresponding to all the aggregate data for whole numbers of days, which you will recall was put in a single record. So to put that in perspective, that would be 7 reads if we were calculating 5 floating rate averages. If I was having to do that over a 90-day period, if the largest floating rate period was 90 days, I'd have to do 450 reads if I had an average of 5 transactions per day. Again, it's a fixed number of reads. The naive solution, actually, the number of reads is potentially unbounded, and so you've got a long tail there, which is the thing that is going to be disruptive with respect to your SLA. So hopefully you can see that what we've done here is really quite significant in terms of optimization. So I'll finally note, I've chosen a specific example that's quite narrow, the example, floating rate averages, but this technique is not simply limited to averages. So any calculation which is susceptible to this type of MapReduce attack can take advantages of the technique that I've described and reduce reads to fixed numbers of reads, which are highly optimized. Mathematical examples of that are standard deviation, variance, max and minimum. All of those can be attacked using a MapReduce type approach. But it's the API that actually allows you to make use of that MapReduce type approach, and key thing about the API is that it has very low overhead. So these operations can be added to your application code without you having to worry about the performance implications. So let's just look back to the agenda to show how Aerospike's list map API can be used to radically reduce recounts. I think we've demonstrated that sort of really quite clearly today, and the fact that it leads to reduced recounts has been made very, very clear. We're certainly not scared of reads at Aerospike. So we're a database which allows you to, on commodity hardware, do reads 95% of the time in less than a millisecond. But sometimes, even if you've got that, you may need to further optimize. The techniques that you've seen today let you do more effectively with very little, and the very little is really the slivers of time that are allocated to us in any sort of real-time processing scenario. So it's these are powerful capabilities that the database is giving you. Okay, well that's everything. So I'd like to thank you for listening, and hopefully we've got time for a question or two.
Thank you, Ken. That was a very informative presentation. We do have a few questions in the chat. If anyone else would like to ask any questions, please don't hesitate to put those in the chat too, and we'll get Ken's take on whatever the questions are. So, Ken, the first question is, listening to your talk, it strikes me that the CDT API would be useful for organizing time series data. It gives you records within records and lets you incrementally update aggregates. Would you agree?
Yeah, I mean, I'd absolutely agree with that, Tim. So in the customer deployments that we have, amongst them are a number of time series based deployments, and the CDT API is absolutely key to our being able to support those. In fact, we had a talk yesterday from G-Research relating to time series, and a substantial component of the work that they're doing makes use of the CDT API. It's worth checking out that talk if you didn't have the opportunity to listen to it. One thing that came out of it for me is that not all time series use cases are created equal, and the nice thing about having an API is that you can model things as you would like them modeled, and you can program things as you would like them programmed. And a question that one member of the audience had for Stephen is, well, why didn't you use an off-the-shelf time series database? And the answer, well, there are a number of reasons, but one of them was that it didn't give G-Research the flexibility that they felt they needed. And a secondary component of the answer was that a lot of time series databases aren't actually distributed systems. So when you're talking about very large scale use cases, then actually, you've got another dimension to consider. So, I guess a number of things that Aerospike has really help support time series use cases, but the CDT API is absolutely critical.
Great, thanks, Ken. The next question is, would I be right in thinking that you can use the CDT API to manage documents? Jason, for example.
So that's quite a perceptive question, actually. So I'm guessing that that's come from a member of the audience who perhaps has used Aerospike already. Yes. So as you could see from the examples in the presentation, you can put together essentially objects of arbitrary complexity, composing them using lists and maps as primitives. And if you think of JSON, effectively, it's an assembly of list and maps, nested to a potentially indefinite extent. So we've got all the key things which let us sort of successfully and precisely navigate documents, so creating them in the first place, but reading specific elements, updating specific elements, reading ranges within the document. And as it happens, we've got a document API on the way, so stay tuned for that. As I said, we've got the primitives, but wouldn't it be nice if you just kind of wrap that up and put a little bow on top of it and just made it kind of that bit easier for people to start. So what's the idea behind that is, well, wouldn't it be nice to manage documents using XPath-like expressions? If you're familiar with XPath, something which looks like a file path and lets you naturally traverse the document. So that API is on the way, but under the hood, it's using the CDT API. So good question, and sort of stay tuned for that.
Perfect, thanks. And the final question we've got in chat at the moment is, you didn't really talk about the AI modeling side of things. Would you be able to say something about that?
Yeah, absolutely. So I guess focused on just being very efficient. I guess kind of the trend in fraud reduction is towards very much using machine learning, because machine learning effectively allows us to adapt effectively instantly to the data that's coming in. There's two elements to probably machine learning in any context, but maybe fraud reduction in particular. There's the creation of the model, and there's the deployment of the model. The part of it that I feel gets the most attention is the generation of the model, because if you will, that's where the sort of new technology and the new approaches come in, the ability to effectively spot patterns automatically. But if you will, that's less important when we consider the real-time aspect of what people have to do with fraud reduction. So, when somebody makes a payment, you basically need a yes, no, or maybe decision effectively instantly. The models that get created are created by and large in a very naive fashion. So there are techniques for making them less naive, but if you will, you throw all the data you have at the learning algorithm, and it picks out the bits that it likes best for itself. But you don't know without pruning which bits of data will be the useful bits. So the models that get created are often quite hungry, right? They're so quite voracious, if you will, in terms of the amount of data that they need. So when you deploy one of these models, it quite often will take a very large number of inputs, and unless you can obtain the data that you need to feed the model in the time window that you have, then your new sort of sexy 21st century method is absolutely dead in the water. So while efficiency might not seem like the exciting end of things, it's absolutely critical to making machine learning a success in a context such as fraud reduction.
All right, perfect. Thank you, Ken. There don't seem to be any more questions, and we're right at time. So again, thanks once again for a great session. And to everyone listening, thanks for attending Ken's session at User Summit. Hope you've had a wonderful summit. Looking forward to seeing you on other sessions. Thank you.